Good morning, everyone, and welcome to a second talk on the series, not really, but on cosmic organization in the HRST universe. Last week we had Nick Nedin, who gave more of a theoretical perspective, and today we're hearing more about observations from Pascal Oesch. So he's an assistant professor at the University of Geneva, and after spending some years in the US as a Hubble and then YCAA Prize Fellow at Santa Cruz and Yale, but his PhD is from Switzerland as well, from Zurich, the ATH, where, and so he's back to Switzerland. And we know that he's a famous Swiss person because he shares the birthday with Roger Federer.
All right.
So there is not much fantasy about choosing dates of birth in Switzerland. It's like the cuckoo clocks.
That's right.
Anyway, so we will hear more about the HRST universe and galaxies with the galaxy built up at cosmic dawn, Hubble's legacy into the JWST era.
All right. Yeah. Bonjour à tous. Thank you very much for the invitation. And yeah, so I'm going to be talking about some of the work that I've been doing over the last, almost a decade now, using the Hubble Space Telescope and actually, now looking forward already to what the James Webb will be able to do. And so that's work, of course, in collaboration with lots of people over the last few years. I particularly want to highlight Richard Bowens, Ivo Labbe, Garth Illingworth, and that kind of team. And so together we're using Hubble data to try to answer some of these questions: when and how did the first galaxies form, and how did they grow and build up their mass as a function of time from the very early universe. And over the last few years, 28 years that we have Hubble in space now, we've of course made great progress in understanding galaxy buildup through images like this. That is the Hubble Ultra Deep Field that we are flying through. So we have multicolor images, very deep, high spatial resolution, and we can therefore really trace the buildup of the galaxy population out to, very distant. Here, this red dot is one of the most distant galaxies in this particular field. And so when Hubble was launched in 1990, essentially we only knew about normal star-forming galaxies up to redshifts of around 1. So that's redshift here. That's about halfway back to the beginning of the universe at 13.8 billion years here. And so, again, I'm one of the astronomers that cannot imagine astronomy without the Hubble Space Telescope. And in particular, I can't imagine how it must have been when this first image came out, when the WIF-PIC 2 camera was installed on Hubble. And the Hubble Deep Field was observed, and it was then clear that the universe was full of galaxies, of course, and in particular with the Hubble Deep Field in 1995, astronomers were able to look out to redshift of about 4. So that's 1.5 billion years after the Big Bang. And then with every succession with the servicing mission, with every update of the Hubble cameras, we were able to push further and further back in time. And so now in 2004, when the ACS camera, the Advanced Camera for Surveys, was installed, together with NICMOS, so this is the Hubble Ultra Deep Field, the famous image, then we were really able to go to redshift 6 and 7. And now, with the last servicing mission in 2010, when the WIF-3 IR camera was installed, now we're really able to probe out to redshift 10 and 11, as I will show. So with every servicing mission, we were able to push further and further back in time. And so I really like this quote by D. Hubble: "The history of astronomy is a history of receding horizons." And that's, of course, exactly what perfectly encapsulates what the Hubble Space Telescope has been doing for us over the last, essentially 28 years. And as I will show, again, with the new camera, or new, now it's also 8 years old, we've been able to really probe, again, into this epoch of reionization, which is an important epoch here beyond redshift 6. And as I'll show towards the end of my talk, this is now the most distant source that we found in some of these Hubble fields at redshifts of around 11. And so again, Hubble has really been pushing our cosmic frontier further and further back in time. And so now, it's really very interesting to sort of step back and to see where do we stand now with with the Hubble legacy, essentially, as we move into the JWST era, of course, in the next year or so. And you know, see what can we learn about the galaxy population before we move forward in the future towards really the cosmic, to the first stars in the universe. And so before doing this, I want to quickly do a little bit of early cosmic history. And so in particular, the history that I'm studying here is really the first 1 billion year of cosmic time. And that was, of course, a very unique time. A lot of things happened for the very first time and for the only time in cosmic history. And so we're starting here with the CMB, with recombination, 400,000 years after the Big Bang. And so at that point, of course, the universe was really neutral and dark. So there were no sources of light. And it took about 100 to 200 million years, according to models, for the first gas clouds to be able to collapse in dark matter halos to really then form the first generation of stars at redshift 20 to 30 or so. And so these stars, of course, were very massive. That's what theory tells us. And so they were evolving very quickly and rapidly went supernova and started to pollute the intergalactic medium around them with the first metals. And so these metals really set the stage then for the formation of the first galaxies. We could cool the gas much more efficiently. And so quickly after the formation of the first stars, we expect the formation of the first galaxies. And so then, as these galaxies and stars started to grow, they started to emit ionizing radiation. And you can, that's sort of illustrated here. These galaxies produced Strömgren spheres around them of ionized gas. And as more and more of these galaxies started to form, at some point these ionized bubbles started to overlap, and that's what we call reionization. So the last major phase transition, we're going from a neutral to an ionized intergalactic medium at this redshift of around 6. And then after that, of course, we have the buildup of today's galaxies. And so what I want to do today is really look at the galaxy buildup in this time here at the end stages of cosmic reionization and really push back as far as we can with current facilities. And so in general, there have been sort of historically two kind of techniques to identify very distant galaxies. On the one hand, we have Lyman alpha emitters that, effectively, if you have a very young, low metallicity galaxy, up to 6 to 7% of its total luminosity can come out just in the Lyman alpha line. So it makes sense to start to look for that. And so effectively what you can do is you can use a narrowband filter and place that in a dark region of the sky spectrum. And you can then look for an excess in this narrowband filter compared to the underlying continuum. And so that's what has been done extensively, in particular redshift 6.6, for instance, where you have one of these windows. And the nice thing then, of course, is through this narrowband selection, you can then do spectroscopic follow-up. And because you're selecting based on a line, you actually often get, of course, a spectroscopic confirmation afterwards through these beautiful Lyman alpha lines. The main problem with this is that you can only select galaxies in a very narrow redshift range, right, where you have these narrowband filters. And so the other technique then that we've been using, in particular with Hubble, is the so-called Lyman break technique, where even after the epoch of reionization, you have still pockets of neutral gas in the intergalactic medium. And so these neutral gas clouds, they absorb in the rest frame Lyman series. And so that causes an intrinsic spectrum of a star-forming galaxy that looks like this, that causes, this absorption causes a Lyman alpha forest, and then complete absorption shortward of 912 redshifted. And so you can use broadband filters to place these filters across this Lyman break, and so you can then easily select galaxies over a relatively broad range in redshift through this so-called dropout method. And so that's what we're doing with Hubble, because we do have lots of broadband photometry on it. And so here I'm showing the filter set that we have with the Hubble Space Telescope, going from the optical with ACS into the near-infrared. And so this is an intrinsic spectrum of a galaxy. Below here you see how it would look like in an image. And so now we're pushing the redshift further back And what you can see is that the Lyman alpha break here gets stronger and stronger. And by redshift 7, at this point, we're now really in the neutral era, so we're in the epoch of ionization. So essentially, you have complete absorption short of the Lyman alpha line. So it's not the Lyman continuum break, but the Lyman alpha break. And what you can also see then, of course, is that these galaxies completely disappear in the optical ACS images. So the original Hubble Ultra Deep Field did not contain any galaxies beyond redshift 7 because of this intergalactic absorption. And so that's why it was so important to probe longer wavelength with the V3IR camera. And then you can see as we let this run forward or backward in time up to redshift 12. That's really the limit that we can probe with Hubble, given the wavelength coverage that we have. And so beyond redshift 12, we need a new telescope, and that's, of course, James Webb, just because the galaxies, again, disappear from our sensitivity limit. And so this kind of data we now, as a community, have collected over the last few years over large areas. And essentially, we have this multi-tiered data set that we can use for this kind of high redshift studies to select galaxies in this particular way. And so that includes several surveys, in particular the Hubble Ultra Deep Field that we were flying through in the beginning. That's embedded, so that's the deepest image that we have of the universe. And that's embedded in another larger survey, which is called the Candle survey, that is probing wider area, but shallower imaging. And then we also have deeper parts within that survey. So it's a multi-tiered data set on its own. But then we also have other images, for instance, the Clash survey and also the frontier fields that make use of lensing magnification of foreground clusters. And so you can probe intrinsically fainter sources because of the magnification over small areas. And then there's also pure parallel programs such as Borg. And so over the last few years, we have then been collecting all these, or analyzing all these data sets and looking for these distant galaxies. And so this is, by 2016, this was our census. Essentially, we have more than 13,000 galaxies, or 12,000 galaxies in these Hubble fields, particularly in the blank fields, so not including the lensing cluster fields. And so here you see this is log number as a function of redshift. And you can see how, again, this is log, so how this number density decreases quite rapidly. So that's, of course, due to two effects. First, we're looking further back in time, so more distant galaxies, but also intrinsically, the galaxy population is becoming fainter and fainter, so it's shifting across our detection threshold. And so then you can see here, the other thing in the blank fields, these number counts are really dropping off a cliff here beyond redshift 8, and that's mostly because of the filter set that we have available on these kind of fields. And so now with the Hubble frontier fields over the last year or so, we've been working hard to really build up, in particular, this most distant galaxy sample, where we have still very small numbers. So all in all, we have about 1,000 galaxies in the epoch of ionization. And again, the current frontier is really at redshift 9 to 10 based on these data sets. And so with Hubble, we're identifying the galaxies. So that's, of course, really crucial. That's at the core of our analysis of these galaxies. But the problem is with Hubble, we only get this very, very narrow range in the spectrum of these galaxies, right? Only the far UV. That's where we detect these sources. And so it's really important to have this combination of other facilities to get a much more comprehensive view of these early galaxies. And so, for instance, I've been taking a lot of near-infrared spectra to, in particular, look for red stream UV lines with ground-based telescopes. With Spitzer, we can probe the red stream optical emission of these galaxies, 3 to 5 micron, essentially. And so that's really crucial, of course, if you want accurate stellar masses for these galaxies. While with Hubble, we can only probe the unobscured star formation. And also, as I'll show, we can actually get quite interesting constraints on the red stream optical emission lines just based on the broadband Spitzer photometry. And then the new telescopes, of course, that we're all excited to use is ALMA as well as NOEMA, of course, that for now finally is able to probe sort of the dust process, the emission, so the UV photons that are absorbed here that we don't see in Hubble, we can now probe in ALMA, so really closing the energy balance, and also probe atomic and molecular gas in these galaxies. So for the combination of these different data sets, what can we learn about this early galaxy population? And so I'm just going to go through a few science highlights in this part here. And the first thing, of course, that we can do just based on the Hubble data is, count these galaxies as a function of redshift. And so that's the UV luminosity function up to redshift 8 now here. And so this is, again, the number of sources per bin in luminosity. So this is from our team here. We're going now from redshift 8 here in red, so that's about 650 million years after the Big Bang, up to 1.5 billion years after the Big Bang at redshift 4. And so here we have the bright end, the faint end, and about the 7 magnitude baseline that we can measure this over now. And so there's two things that you should take away from this. On the first part here, you see there's a really well-defined build-up, essentially. We're going from redshift 8 here. You see how the number density at the given luminosity essentially is increasing effectively by a factor of about 2 per unit in redshift. So the galaxy population and also the star formation rate at that point is really increasing quite dramatically over this time. Then the second point is that the slopes that we're finding here are extremely steep. And it turns out that they're actually steepening as a function of redshift. So as we go up in redshift, these slopes become steeper and steeper. And effectively, that means that there's a huge amount of the UV light that is below our current detection limit. So that is below here in even fainter galaxies. And so what this means, again, is that we're essentially only seeing the peak of the iceberg. And there's a huge low luminosity galaxy population out there. And so over the last year or so, people have been, again, using the frontier fields, so the lensing magnification from clusters to probe even further down to try to, see a bit what's down there below the tip of the iceberg. And so essentially, using this lensing magnification, we're able to probe down essentially 3 magnitudes fainter than what we have been doing with the Hubble Ultra Deep Field. And essentially what we're looking for here is a turnover in the luminosity function. So this is predicted from simulations. Again, this is a luminosity function. And you see how there's a predicted turnover because essentially you're not forming stars in these very low mass halos or not efficiently. And after ionization, you're also photoevaporating some of these halos. And so essentially, what we're seeing here, so this Hakim Atek also has these blue points are from his work. Essentially, we're probing 3 magnitudes fainter. The luminosity function at that point is still steep and is still continuing steep. And then below that, again, we're probing down to -13 essentially here. The uncertainties, because of the lensing magnification, these are systematic uncertainties, they essentially blow up. And so the problem is that the volume corrections or the completeness corrections depend on, for instance, the size of your galaxy, depend on the shape of your galaxy. And also the uncertainties from the lensing models themselves. So at the moment, we cannot really, determine whether there is a turnover or not. But it is definitely clear that the luminosity function keeps on going steep down to essentially -4. And so there's at least an equal amount of luminosity below, for instance, the UDF detection limit than what we can see now with the frontier fields. So a lot of faint, ultra-faint galaxies out there in the early universe. And then the other thing that we're kind of surprised about is when we were looking at these ultra-faint galaxies, again, that we can probe in the frontier field. So these are absolute magnitudes of -15 or so. We were seeing that they're essentially, extremely small. So we knew already at the bright end, so this is sort of stellar mass, so converting the UV luminosity to a stellar mass versus radius here. So these are the redshift 6 galaxies around here. Then we have other galaxy populations, other types of galaxies at lower redshift populated here as well. So essentially what we knew that the the brighter galaxies were of order of a kiloparsec in size in half-light radii. But as we were probing fainter, and in particular as we were probing in these high magnification regions, we expect there's going to be a lot of shear in these frontier field clusters. And so if you look at some of these galaxies, so these are redshift 5 to 7 galaxies that are lying in a very highly magnified region where we expect a lot of shear in these galaxies, they look extremely compact. So no apparent extension at all. And so you can then compare this with the simulated or the expected shape of these galaxies. Again, because of shear, you expect a factor 12 or so extension in one direction. And the intrinsic half-light radii, the only thing that really matches these kind of things are extremely small sizes, less than 100 parsecs for these galaxies. So effectively, what we are potentially seeing here is essentially globular clusters in the making. So if the shaded region, so the open circles here are globular clusters. The shaded region here are sort of star-forming clusters in the local universe. And you can see effectively we're seeing individual globular clusters or star-forming clusters in these galaxies. And so again, that's a very interesting new avenue, and we're definitely going to pursue this further with, again, James Webb, where we have better spatial resolution, of course, and also taking spectra of some of these galaxies. Okay, so far I was only talking about photometrically selected sources, again, using this Lyman break technique. And the problem is, of course, if we look at the spectrum, at the UV wavelength here of a high redshift galaxy, or of a star-forming galaxy here, you see the most prominent feature that we have in a galaxy like that is the Lyman alpha line, as I said before. And so it's not surprising, essentially, then that the Lyman alpha line really was driving the spectroscopic confirmation of all of these distant sources, essentially. And so you can see here, for instance, as the year of discovery, the spectroscopic redshift record, as a function of time, and all of these after 1985 essentially are based on Lyman alpha. And again, the main problem then is, as we're moving into the neutral era of the universe, so beyond redshift 6, it turns out that the Lyman alpha line is disappearing because, well, we're in the neutral era. So we have a star-forming galaxy embedded in a neutral gas, in a neutral intergalactic medium. So that intergalactic medium will absorb the Lyman alpha line through its damping wing. And you can see this here. So this is the fraction of galaxies, Lyman break selected galaxies, that do show Lyman alpha with an equivalent width of 25 angstrom or stronger in emission as a function of redshift. And there's a clear drop as we go beyond the redshift 6 sort of boundary. And so again, that's an imprint of cosmic ionization because of the neutral intergalactic medium. So people have been using this drop as a measure of the neutral fraction. But of course, it is difficult then to confirm some of these sources with spectroscopy, right? And so it's interesting that really only the brightest sources that we have found in the Hubble datasets currently have spectroscopic confirmations. And so, again, this is through the Lyman alpha line, typically. So we have a sample of kind of 5 to 6 very bright galaxies beyond redshift 7 that we have been taking spectra of, and this is one of them, redshift 7.73. And the interesting thing is that then with this particular galaxy, we also followed up with Dan Stark and collaborators in C3, and so this was detected in carbon-3. And so this is effectively, I think, still the most distant galaxy with a multi-line spectroscopic redshift. But what is even more interesting, of course, is that we detect this carbon-3 line, and this has a very high rest frame equivalent width of 22 angstrom. So some of the brightest or the strongest carbon-3 emission. And so this implies a very strong radiation field and also low metallicity for some of the brightest galaxies at redshift beyond 7. And so it turns out that this strong radiation field is a general feature of high redshift galaxies. And essentially what we're seeing this also, for instance, in Spitzer colors. And so here these are the SEDs of redshift beyond 7 galaxies, again, that do all have spectroscopic redshifts through Lyman alpha. And so we know exactly, of course, what these Spitzer colors are probing. So here I highlighted the Spitzer photometry, and you can see in all of these cases that the 4.5 micron flux is definitely significantly enhanced towards compared to the 3.6. And because we do have spectroscopic redshifts for these galaxies, we know that the 4.5 micron band is exactly where oxygen 3 and H beta lines are lying. And so these are strong, extremely strong lines that are contaminating the 1 micron wide Spitzer photometry. And so it turns out that this is a very general feature, not just of the brightest galaxies, but really of the average galaxy at redshift 7 to 8 or so. And you can see this here. Again, this is a stack of the total galaxy population that we have. This was from 2013, but you can see again from so redshift 7, you see this color here, because O3 and H beta lie in the 3.6 micron band. And then just slightly higher redshift 8, you have the complete inverse color. And so you can work out the average equivalent width based on this color difference, and it turns out that this is of order 700 angstroms rest frame for these lines. And so this is extremely strong, of course. In the local universe, we have an extremely small fraction of galaxies showing such strong lines, and the question then is how can such strong lines be produced in the average galaxy population? And you can, again, see the same thing here if you plot the 3.6 to 4.5 micron color as a function of photometric redshift. And you can also indicate the redshifts where different lines move in and out of these color bands. And you can see how this color really it wiggles up and down just because the different lines are pulling the color in one way or the other direction. And so we have extremely deep data from Spitzer, which is the great survey led by Ivo Labé. We have 200-hour exposure times, in particular in the goods fields. And so you can see that even at redshift 8, you can detect, and this is an age of 28 magnitude galaxy, you can detect it at 4.5 micron with this very deep imaging, but just because we're seeing this extremely strong O3 and H beta emission line. And so the median here is overplotted here with this thick line, the median color as a function of redshift. And you can compare this then to models, to see what are the kind of typical properties that we need for reproducing this kind of color. And you can see that on average, the galaxy population it seems to be very young. So you can reproduce the median color very well with a 500 mega-year-old population. But the extremes that we're measuring here, it definitely needs an extremely young stellar population with quite extreme conditions. And we can zoom in on a redshift 7.5 here and look at what the colors are there. So the median color at that point is about 0.4. And so we're using a relatively large grid of cloudy models and BPAS SEDs to then try to interpret what these colors are. So Jacobo was doing a very similar thing in the UDF. And so essentially what we're seeing here is, again, so this is the color at redshift 7.5 as a function of stellar age now. And then different lines are different ionization parameters, different metallicities here, 20% solar or 5% solar. And what you can see here is that the median color you can actually reproduce, again, with sort of youngish stellar population, but definitely it needs high ionization parameters, otherwise you will never get to the median color like that. And relatively low metallicity, but not too low, because otherwise you don't have enough oxygen. And so that's work by my postdoc that is in prep. And then the more extreme sources, again, you need the extremely young stellar populations. So that's good. I mean, we can start to make some progress just with Spitzer. Of course, we will want James Webb for this. The point is, though, if we have these extreme colors, and in particular, if we go back, if you want to now measure a stellar mass, again, we need the rest frame optical emission for these galaxies. The problem is that you have the Spitzer photometry is the only thing we have to do this, and at certain redshifts, there's again these strong rest frame optical lines that we have to account for to do stellar mass or estimates or SED fitting. And so doing this, people have been, statistically at least, taking this into account. And so we can then, again, accounting for these terrestrial optical lines, we can start to measure the buildup of stellar mass. So this is the mass function from Mimi Song's work from redshift 8 to redshift 0, essentially. We also see that as a main sequence of star formation is already in place, redshift 4 to 6. So these are the kind of things that we can start to probe, again, with relatively large error bars, both because of the low number of sources, but also, again, because of the uncertainties in the SED fitting. But putting this together, essentially, we can see what is the buildup of star formation and stellar mass in galaxies, again, from Hubble and Spitzer photometry together. And so this is, I guess, the review by Piero Madao and Mark Dickinson. So it is showing the cosmic star formation rate density as a function of redshift. And as I said, from the luminosity function, we know that the galaxy population from redshift 8 to 4 is really building up very rapidly. And you see, of course, that this continues up to redshift 2. So a factor of about 2 per bin in redshift, and more than order of magnitude from redshift 8 to the peak. And so then this line here is a fit to this, and you can then compute, okay, what is the mass that you were building up during that time? And so that's, again, this line here. This is the mass density as a function of redshift that is being built up through the star formation that we're seeing. And at this point, there seems to be really quite a good match. And again, because the star formation rate is increasing over this time, the stellar mass density, of course, is also increasing and building up extremely rapidly in these early galaxies. Okay, so this is a very nice plot, of course. I'm sure you have seen this 10 times before, or probably more. The problem is, though, that the plot stops at redshift 8. And so I really do not like that. The question is, how does this evolve beyond redshift 8? And again, as I said, we can probe redshift 10 galaxies with Hubble. So yeah, let's do that now. And the reason why I guess this is not on their diagram yet is, while at redshift 7 to 8, from different teams, there's been really quite a good agreement now on the luminosity functions and therefore on the star formation rate densities. At redshift 10, there's been still quite some uncertainty in the literature, mainly, of course, because the samples are extremely small. So even with Hubble, it's extremely difficult to find many redshift 10 galaxies, and so that led to some discrepancies in the luminosity function determinations of factors of 3 or so. And so, yeah, so over the last, I guess 5 years or so, I've been really trying to find, to exploit all the Hubble fields to find, the largest sample that we can of redshift 10 galaxy candidates. And so, but again, this turns out to be really, really difficult. Even in the Hubble Ultra Deep Field, again, where we have the deepest image of the universe, we only found this one little candidate here. It's a 30th magnitude source, but again, there's only one in there. And then even in the wider area fields, in the Goods fields, for instance, we only find one additional, in Goods South, one additional source. Then in Goods North, we found 3 galaxies. Turns out all of these are about 3 magnitudes brighter than the one source in the UDF. So there's a little weird luminosity function. And then nothing in the other candles wide fields. So with Hubble, we're really, redshift 10 is really the limit of what Hubble can do, it seems. And so then, the frontier fields came out, of course, and we were all super excited about this data set, and in particular, the first cluster that was taken. So the frontier fields are 6 clusters, 6 parallel fields. And the first cluster that was taken, Abel 2744, already contained this beautiful, triply imaged redshift 10 galaxy candidate. And you can see this here. So these are the two brighter images, then there's a fainter one potentially down here. And again, it has a very similar magnitude, demagnified magnitude to the one in the UDF, but is of course magnified by factor 10 to 11 or so. The nice thing about this source here, of course, is if you have this multiple imaged candidate, you essentially get a geometric constraint sort of on its photometric redshift because of the position of these 2 galaxies, of these 2 images of the same galaxy with respect to the critical curve. You essentially get a geometric constraint on the redshift. So it's a very good candidate for redshift 10. And so yeah, we were super excited, and we were really looking forward to the next 5 clusters. But yeah, so it turns out that this was the only Redshift 10 candidate that I could find in this field. In the cluster fields, there's 2 more galaxies in the A370 parallel field, so not really using the magnification. And so, yeah, so over the last few years, combining all these data sets, effectively we only have 9 reliable Redshift 9 galaxy candidates. Again, with Hubble, we're reaching the limit of what we can do. And so, yeah, let's see where we lie then. We can look again at the cosmic star formation rate density and see, now put this point here at redshift 10. And yeah, so let's see. So again, we're expecting many more sources, finding only 9. Essentially, that means that the star formation rate density is really dropping off very, very quickly. By an order of magnitude in only 170 million years or so, from redshift 8 to 10. And I've been saying this for a few years now, so I think I'm already in this room. So, but it has been confirmed now over the last 5 years. I could not find more sources. And so, why do we find so few galaxies? Essentially, it's not really surprising. If you look at the halo mass function, that is also evolving very, very rapidly over this time, and in particular over the mass range, of course, where we expect these galaxies to sit in. And so it's a slightly complicated plot, but it's the star formation rate density at high redshift. Again, these are the redshift 4 to 8 measurements that are really evolving rather smoothly, and then we're finding this relatively steep drop to redshift 10, and it's been confirmed by other teams as well now. Again, but if you look at the halo mass function, so this orange line here shows just the number density, the cumulative number density of halos above 10 to the 10 solar masses. You see that, and then normalized at redshift 8, and you can see that that number density also declines really, really quickly. And so, yeah, it's not surprising necessarily that we're finding this very steep drop. We can also do this a bit more quantitatively. We can measure, even though we only have few galaxies, we can measure a luminosity function, even though the error bars are large. But we can compare this then to all kinds of simulations and semi-empirical models and semi-analytical models and so on. So the redshift 10 universe, not for observers, it's not only exciting for observers, but also for theorists now, of course, with James Webb on the horizon. So there's many models out there that predict the redshift 10 luminosity function. And so here you have the redshift 8 luminosity function here. This is our measured luminosity function redshift 10. And then these colored lines here in blue and green are the models. And so you can see, first of all, that the model curves agree rather well, I would say, between a factor 2 to 3. So that, and all of them predict a very significant decline from redshift 8. So that's definitely clear, again, because of the halo mass function that is evolving rapidly. But what is interesting is that we are definitely at the low end of the model predictions with what we're finding right now. And we can do this even we can illustrate this even better. Essentially, we can take these model luminosity functions here that are plotted here. We can put them in our through our selection volumes from all the different fields together, and we can then predict how many galaxies would we have seen if these models, each of these models were representing the truth. And so you can see this here. This is the number of candidates, the number of redshift 10 sources that were predicted by these models. And these are just different models here. The best fit luminosity function, well, the one we're measuring is 9 sources. That's what we found, of course. And you can see that there's kind of two. So these are empirical models, and then here we have model predictions from semi-analytical hydro simulations and so on. And so there's kind of two model classes. Essentially, there's a bunch of models that predicted about 30 galaxies, so that would have been nice, but unfortunately that doesn't seem to be the case. But then there's a whole bunch of models that definitely were within 1.2 sigma range or something like this of the prediction, but again at the low end, unfortunately. And so the question now is, well, we're just unlucky with the data sets that we have. It's still a limited survey, of course, all these Hubble fields together. But yeah. it's interesting to see that we're at the low end of the predictions. And the question then is, okay, what, is this a problem for moving forward with James Webb? And I don't think so. Again, the interesting thing is so I was working with NICMOS and I was looking at these Redshift 7 galaxies with NICMOS, and then we got the V3 IR camera, and that was really a huge push forward. Again, from 10 years of observations with NICMOS, we found only about 12 galaxies, and essentially in the first week of observations with the V3 IR camera, we found double the number of sources, and it was really amazing to see these first images. And so, but now in the next future, we're going from V3 again to James Webb, and at Redshift 10, again, where we are struggling now with Hubble, it will definitely be a huge increase in the number of sources and in the quality of the images that we will get for these. And so here I'm just showing, again, the number of galaxies as a function of redshift. Again, it's declining very rapidly in the HST fields, and these are some model predictions. Again, we have in the blank fields about 750 square arc minutes, and now we can see, okay, what will we expect for, what number of sources will we expect in a James Webb field using the same kind of area, but going 2 magnitudes fainter, right, because of the efficiency in the near-cam imaging. And you can see this here. So yeah, again, there's essentially, depending on the model, an order of magnitude increase in the number of sources. So there will definitely be a huge population of galaxies out there, and depending on which model, again, you look at, we will definitely reach beyond redshift 14, and so really starting to probe into the dawn of galaxies. Okay. So in the last few minutes, I just really want to look at, are we really finding, Redshift 10 galaxy candidate, are these candidates actually at Redshift 10? And so, unfortunately, again, these are very faint, and so it's impossible to do spectroscopy from the ground. But the brightest sources of these, it's this galaxy here, a 25th magnitude source, had a photometric redshift of 10.2, yeah, was within reach of the Hubble GRISM spectrograph. And so we were awarded 12 orbits of Hubble GRISM spectroscopy. So the V3 camera also has a GRISM mode, and so you can essentially, you get, you put this GRISM in, you just disperse the whole image. The problem then is that you disperse the whole image, and so you get a spectrum for every single galaxy, and these all overlap. And so you have to make sure that for these kind of GRISM observations, you choose the orientation angle properly, and you have to really model all the contamination along the dispersion direction, and so we did that here. There have been previous spectra from the Agathe survey where you can see the contamination over the spectral range where we're interested in for this Redshift 10 galaxy candidate was very high. And so we were modeling all this, subtracting the neighbor contamination and in this 12-orbit spectrum. And so this is what we found here. So this is the 2D spectrum on top, the 1D spectrum on the bottom, extracting this flux here. And you can see that we significantly detected a continuum for this galaxy here. And so that's a 5.5 sigma detection when you integrate it. And individually here, per resolution element, we see a 1 to 1.5 sigma detection. And so, it's not great, but you definitely, again, see there is a spectral break in this galaxy. And again, this is the Lyman alpha break that we've seen in these kind of simulations before. And so we can fit the redshift for this source, and it turns out to be 11.1 plus minus 0.1. So yeah, the redshift changed, and so the name had to change as well. So now this is GNC11. And yeah, so it's the most distant source that we've seen so far, but it does, again, it's a spectroscopic confirmation in this sense. It does prove that there's the buildup of massive galaxies was well underway already here at 400 million years after the Big Bang. And so is it crazy to find one such galaxy in the Hubble fields? Well, no. It turns out that essentially the physical properties of this galaxy that we infer, again, from the Hubble and Spitzer photometry together, are in perfect agreement with what models would have predicted for a bright galaxy like that at redshift 11. And so these are the Dragon simulation. These are the blue tide simulations. So for instance, here, let's look at this diagram. This is the absolute magnitude that we have of the source, minus 22. Then here we have the stellar mass, the star formation rate, and also the age that we have very uncertain, but some constrained on. And you can see, again, our measurements lie exactly on the model predictions, essentially. And so that's in very good agreement with the expectation. The main problem is that the number density just doesn't work out. So effectively, finding one such galaxy in the candles field is really quite unexpected. Effectively, using the previous luminosity functions that from the model predictions that I've been showing you, would have expected that we needed at least 10 to 100 times larger area to find this particular galaxy this bright at redshift 11. And so, I don't know, does this tell us that there's something new fundamentally going on with early galaxy formation? Well, probably not. We only have one galaxy, of course. It's very difficult to draw any conclusion based on one such galaxy. But yeah, we would definitely want a larger survey, going down to this kind of magnitudes. And we don't necessarily want to wait for Euclid to do this. So hopefully with Hubble, over the next few years, we will be able to get more data and really constrain the number density of these bright kind of sources. So if we look now at the source again, and it's super bright. So this is absolute magnitude versus redshift here. These squares are spectroscopically confirmed sources. As I said, from Lyman alpha, we only have the brightest galaxies confirmed at redshift 7 and above, and so that's why GNC11 really stands out, not only as a spectroscopically confirmed source, but really as an individual galaxy, given its luminosity. Anyway, so it's really surprising. I don't think anybody expected that Hubble, when it was launched in 1990, nobody would expect that Hubble would see or even spectroscopically confirm a galaxy at redshift 11. So we definitely reached into JWST territory. But the point is, with James Webb, of course, this will be a whole different game. So only a half-hour spectrum with James Webb, you're going to get a beautiful spectrum, in particular the continuum break. We can measure much better also than, of course, the redshift. But James Webb, in particular NearSpec, will really completely revolutionize this field. Essentially, for all the sources, again, that we have here from Hubble, we can get spectroscopic redshifts with James Webb. And in particular, as I said, we know that these sources on average have extremely strong red frame optical lines, so O3 H beta lines, and these are exactly, of course, the lines that we can measure with James Webb. And so essentially, we will completely fill out this diagram with spectroscopic redshifts, but also, of course, we will be able to measure the physics of these sources. And as you probably know, at redshift 2 to 3 is now where people are measuring metallicities, so the buildup of metals in these galaxies through lines like H alpha O3 or whatever. And with James Webb, again, we will just completely open up this whole range. So from redshift 2, effectively we will go up to at least redshift 6, 7, 8. And so that's really going to be completely revolutionizing our understanding of these galaxies, and we can really, for the first time, probe the physics of these sources. So that's going to be amazing, but in general, I think it's really a golden era, sort of early universe science. We have, of course, ALMA that we're still starting to use for these kind of sources, but then James Webb coming, but then really the first galaxies is a key driver for many of the upcoming missions, and big telescopes, ELT, and of course also with Euclid, again, we can definitely probe the wider area fields to find some of these bright sources. So again, stay tuned over the next few years. That's definitely going to be a major improvements coming up. And so, okay, with this, I just want to quickly summarize my talk. Effectively, we have now very large samples of galaxies from Hubble imaging up to redshift essentially 11. We are, we've sort of reached a little bit into JWST territory, but again, we have limited information at the moment using Spitzer and IRAC, Spitzer IRAC photometry with Hubble. We can still probe the stellar mass buildup over essentially 97% of cosmic history. And then we found this redshift 11 galaxy, but definitely we would like a larger survey to see whether, this was quite surprising to see whether we will find more of these sources. But it does show that galaxy buildup was well underway 400 million years after the Big Bang, and the galaxy population was rising very rapidly. Yeah, we definitely have not reached cosmic dawn yet. So we want to do that with James Webb in the future. Thank you.
So nice work, Pascal. And I'm used to working at low redshift.
Right.
And at low redshift, stellar populations have a large range of ages and the master-light ratios. And then when you go to redshift 1, you worry about selection effects like surface brightness dimming.
Right.
Am I correct to think that at these very high redshifts, the range in stellar ages is so low, so narrow, that we don't have to worry about them? For example, in your estimates of stellar mass and of the sizes of the emission of the Lyman alpha?
Right. No, you should definitely worry about surface brightness dimming. I mean, it's obviously a huge factor, right, at these kind of redshifts. So far, from what we can tell, we're seeing all the light. So essentially, we did some tests with stacking. We did tests with, looking at shallow data. Then we got data from the Hubble Ultra-Deep Field, for instance. We're not seeing any further extension. So it seems that we're seeing all the light. These sources are extremely compact. But yeah, I can. And again, from, for instance, the lensing, we don't see any extension to these sources. But again, that could be that there is like a star-forming knot somewhere, and then you have a lower kind of luminosity or lower surface brightness component that we just don't see. So that's definitely something that we should worry about. And but at the moment, we don't see any indication that we're missing a large fraction of the light. I'm not sure if the master-light ratio is required for this. I mean, any population, right? You would at low surface brightness, you would miss it. So yeah.
Before going on, I just a quick questions following this. How do these sizes compare with simulations? Are these really surprising or not?
So for the brighter sources, they're in
for the
relatively
lensing.
good. Yeah, for the brighter sources, they're in good agreement. But then at the low mass end, I think they're quite surprising. Yes.
Well, I don't know if you have enough line diagnostic between Z equals 7 and 10 or 3H beta to know how many AGN excitation you can.
Right, that's an excellent question. That's why I'm here essentially to work with Marta. Yeah, I mean so you will have the diagnostics with James Webb. At the moment, of course, we have no way of telling. But the point is, I mean, yeah, I guess I was showing this one galaxy with the C3 line. There is now some galaxies, some of these brighter sources that have C4 lines detected, and so I mean, it's reasonable to expect that there's some low-level AGN potentially in them, exciting some of these lines as well. But yeah, it's difficult to tell what is the kind of contribution from an AGN or galaxy population. And yeah, so again, that's why we're here trying to really model this and trying to understand what we can say with James Webb.
Last month came out a paper in Nature where the people claim to have discovered the most distant quasar, and this one is only at 7.5.
Right.
So does that tell us something, that it takes more time to build up massive galaxies like that? Or is it something about the selection effect in the search technique?
I think it's just the area that we can probe. I mean, those quasars are also quite faint, right? And you need very wide areas. I mean, the number densities of these extremely bright quasars are very low. And I'm sure, I mean, I'm not an expert. I'm sure the number densities tell you something about the formation mechanisms of the supermassive black holes and so on. But to find these sources again, the most massive galaxies at redshift 11, they're 26 magnitude, and so there's no way we can get an extremely wide survey for these, in particular because you have to probe in the near-infrared, right? Yeah.
Thank you very much for this very interesting talk. I have a question about the far UV attenuation.
Okay.
Because it is essential to derive for the size, for the EGN, because you have a tourist dust, and so on. So how is the metallicity of your galaxy, and have you some detection in the far infrared? Not mid-infrared, but far infrared.
Far infrared meaning ALMA, for instance, yeah, in the millimeter. Yeah. So there is a few sources that are detected with ALMA at the redshift 7 or so. Yeah, so we're still building up that kind of sample. So at lower redshift, I was working with my student to look individually at ALMA detections, and there we see the dust attenuation law, for instance, the Calzetti law, still seems to hold for the average population. But that's what we're assuming at the moment. So when we do dust corrections, right, for the star formation rate density, for instance, we're using the Calzetti law, the UV slopes, right, and then the IRAC beta typical thing. But there seems to be some interesting thing going on from redshift 3 to, let's say, 6. At redshift 6, for instance, we haven't detected many sources in the continuum, even though we would have expected them to be visible in ALMA, for instance. So that's Peter Kapak's work. Yeah, so it's not so clear what's going on. It could be the dust temperature that is evolving. So if the dust temperature is rising with the ALMA, we're probing the lower tail, and so it's not so clear whether that's an issue or. And so there's programs going on. A large program, Alpine, for instance, is happening, trying to address exactly that. Yeah.
But you also need a model.
Yeah. Exactly. So, well, a model is the MER 99, IRAC beta relation. That's what we're doing at the moment. Yes.
So when you showed the star formation density and the stellar mass density, the latter seemed a little bit on the low side. Do you think there's an issue there, and could it be connected with the fact that one of the fundamental assumptions here is the IMF? I mean, if that were top heavy, as recent observations suggest, that could play a role too in all of what you've said, in fact.
Yes, the IMF is always. We cannot. So you mean here the mass density, or is on the low side, or is it? Oh, you meant in the luminosity functions.
Yeah.
Oh, at redshift 10.
Yeah, right.
Yeah, I guess the IMF could play a role there as well. I don't know. Yeah, I mean. The model predictions, they have a star formation rate, and then we have a UV luminosity, so you need to correlate that. But I'm not sure I don't think that's the main uncertainty. I don't know. Yeah. Well, maybe we can talk about that.
Yeah, but the match on the screen doesn't look perfect. It looks like a systematic effect, possibly, and an IMF change would go in the right direction, wouldn't it?
Right. No, I mean, well, for the overall evolution, I agree. Yes, exactly. But at redshift 10, I don't know. But here, for the overall evolution, I mean, yeah, there's a factor of 2 uncertainty between different measurements as well, though. So, yeah. But I would say overall, it's a pretty good match, actually.
I was wondering if the redshift 11 galaxy is being lensed. Can you rule out?
There is a somewhat kind of brightish galaxy next to it, and so we modeled using an isothermal sphere, and it seems that the magnification is low, less than 10% or so, but we can't really rule it out. I mean, you have to make assumptions about the mass of that foreground source. But I don't think it will. I don't think it's affecting it too much, right? Yeah.
If the faint end slope were continuing to get very steep, then the lensing becomes more important, I think.
Yeah.
If you have some population, the very low luminosity things getting stronger.
Right. I mean, there's a magnification bias in a sense when you measure luminosity function, but that usually, I mean, from the models, you see that only affects even lower number densities, not this one. Yeah.
If there are no more questions, I think we can thank Pascal.
Thank you.